Hi, welcome to my snow day part 2. If you haven't watched part 1, it's mostly about help files, how arguments are set, how to read those help files, and then some handy uses of how to use tab and autocomplete. Strongly recommend it, but if you want to just jump in here, you're welcome to. Just definitely review those tabs. Just start pressing tab all the time. There is a warm up here. I just left it in just to give you some more practice. One of the more challenging concepts is how are arguments applied. I definitely go through this if I were you and practice these questions. Go review that last video if you needed some help with it. There's an answer. You just click onto the next slide. There it is. Pops up through an animation. Here are the learning outcomes for this week. I am going to stop at here. I'm going to stop here today, and we'll pick up on Thursday there. So first of all, we have working paths and directories. There are two main types you need to know about. We have relative paths, which basically don't have a defined starting point. It can change depending on what's known as your current or working directory. Often stood for with WD for the record. So your working directory would be wherever you currently are. So like when you're looking at RStudio, that is what's located here. So whatever that says there is your current directory. But that is where the starting point is. And then we can do different symbols to move from that location. So I can say like from the current directory, go up one. That's what dot dot stands for. In that directory, / stands for directory. Week 01, which would be a directory inside of that previous directory, and then inside of that one. So go up one into the week 01 directory is how that path would translate. So it's a relative path because it depends on where you started. Contrast that to an absolute path, which would be where there's a defined starting point. So here, the tilde symbol stands for the home directory. That is a specific location, at least for my profile, that specific location. The nice thing about a tilde is even though my home directory, well, I'm on my home computer right now, so that's a different path, but like on the EduPod, it's even a different path. Between you and I on the EduPod, we have different home directories. However, if I use the tilde, it's like universal. So it's a really handy tool. So you'll see a lot of my paths start with tilde, which means starting from the base point of the file system, so the / directory, it goes into, on the EduPod, store, and then it goes into my EID. But instead of typing all that out, I type in tilde. So that's an absolute path. It has a starting point. There's several other symbols. Just know tilde stands for home directory. Dot / stands for the current directory. Current directory. Previous directory is dot dot. It means go up one in the file system, and then directory. And then just directory symbol by itself is what's called the / directory. I believe in like the most precise terms. You will sometimes hear people call this the root, although the correctness of that is maybe debatable, but let's not get into it. It's the whole thing. Here's some examples. dir.create. This is making a directory inside my home directory, inside of a directory called inb321g, inside of a directory called week01. Cool. It's recursive. That's just an argument I've added. That means that if, let's say, I was running this on a computer that had never had this directory created, it would create that first. So it's going to be kind of going in step by step and making more directories as needed. So it's a handy tool. If that directory already existed, it'll give you a warning message. And just for the record, I do have all of the code that you're seeing in today's lesson located inside of this script file. So you can just follow along and run all of this code as we go through. When you do, at least through this path section, make sure you're paying attention here to see how that changes. Back to the presentation. So this next line of code is where we're actually setting the working directory. So this is setting the working directory in the home directory, inb321g, week01 directory. And when you do that, it will change that little part of RStudio I pointed at. Now this next one will then go up one directory, which would mean from here into INB321G and then down into week 02. And when you run this line of code, you should see it, see RStudio change its working directory to the week 02 version. I then create in the current directory, so ./ is current directory, a new directory called test directory. And then finally, I more was just demonstrating that file systems do write their file paths a little bit differently. On my Windows computer, whenever I run this last one, it gives me kind of a weird answer. And that's because this path is a little bit strange. So it's because the backslashes is a special character in R. We're just going to have to come back to that concept because it takes a little bit to describe. But just be aware, different file systems do have different ways of describing their paths. You're usually going to be pretty safe using the /. I do not recommend using backslashes. It gets tricky. If you are ever having trouble with writing paths, and I'll be honest, you will. Paths are strangely difficult. They only come up every now and then, but whenever they do, they're really tricky because you can't get started until you get that path correct. And so I have some tricks for you. These are RStudio tricks. You go to the session in the file, the menu at the top, set working directory, and then you can choose the directory. And when you do this, you can literally just go into your computer's file system using like your computer's browser and select the directory you want. And when you do this, it will write the code for you. Make sure you record that code. But once you've recorded that code, then you're good. It helped you write that path. So just to demonstrate this, if I go choose working directory, I could then navigate to where I want it to be. And now if I want this to be my working directory, I'll hit open. And it wrote that code for me. So I need to make sure I copy and paste it up into my saved script file. But that's the trick, is it allows me to get RStudio to write the code for me. Now there's a very similar process where you can use that same kind of interaction where you click on the interface and then you go to this little button, you choose the file you want to import, and then you modify its settings in order to get it to import correctly. And when you do that, it will write the code for you. So when I was in this little video, I was just going through all of that, and then it wrote that read.csv code for me. That leads into how do we get inputs and outputs? Because if we know how to manipulate the working directory, all of a sudden the path to the right location is largely solved for us. So like, for example, if my working directory was already in week 02, I could just say example.csv here, and it would make this file. That's what write.csv does. It writes a CSV file. It would write that file inside my working directory. Read.csv would be the same thing. Read reads the file into memory. And so if my working directory was INB321G, week 02, I could just say example.csv. If not, if that wasn't my working directory, I could use the absolute path and R would still find it as long as it was the right path. Now, let's dive into these very briefly. It turns out that inputs and outputs are really important. And frankly, sometimes for students really new to computer stuff, this takes a little bit more explaining. So just bear with me. There is a difference between data stored in R. So for example, there is an object called iris. Iris is a data frame. It's a big table of data. You're going to see it a lot. It's a common biology data set. It's useful in a lot of different contexts. We're going to use it as a very common example. You're going to get very familiar with it. But it looks like this. It's got some species names. It's got some measurements. They're organized into a big rectangle. Cool. Well, write.csv is a function, which if you watch my previous video on how to open up help files, it writes data to a CSV object. So it is a version of write.table that's specific to just CSV files. comma separated values. So the syntax for this is there needs to be an X. Oh, let me move my head. There needs to be an X argument. My little auto framer messing me up. There needs to be an X argument. There needs to be a file argument. And so this becomes X because of the order. This becomes the file because of the order. And so in the end, it's going to make the data stored inside of Iris the file called example.csv. And if I run this and I go to my files, there it is. It happened. And if I click on it, I think I've opened it, but that's not right. Look, it's just a bunch of text. It's not been interpreted. It's not been structured. Had I cleaned up my environment before running this, because I'd previously run this, nothing would have happened over here. And that's because it's not been structured into memory in R. It's stored as a file. That's great. That means this data doesn't go away, that I could restart R, I could close it down, I could restart my whole session, I could restart the whole dang computer, and this would still be here. But if I want to use this file inside of R, it can't use that file directly. That file by itself is not a data frame. That file by itself is just a series of letters and occasionally a line break. That's not enough. It needs to be structured. And so you're going to hear this concept a lot of data structuring. We have to give order to it. We have to give it properties. We have to give them like column names and row names. And we have to tell R how many columns there are and how many rows are there and what does each column hold? Like what kind of data? Is it numbers? Is it letters? Is it complicated? All of these things have to be resolved somehow. And so we have a bunch of different tools for doing that. We have our input functions. So like read.csv, it reads the files and it structures it into code. Now, there's a couple of things. Now, the version of this that you have doesn't look like this. I ask you to fix it. And so I'm just going to erase it. I'm going to show you how you can very quickly write code to import data. So there's a video here. This video goes through it, but you import your data set. I'm going to click onto this. I'm going to select the file I want to import. I'm going to change settings. There's one that kind of matters, that there is a row names argument I may or may not need to choose. This one does have a row names column, and so I'm going to use the first column. Other than that, I want the name of my object to be exdf, just to match the rest of the code. And now I'm going to hit import. When I do that, this pops up. And first of all, I can tell that this looks good. I can even sort it. I can explore the data a little bit. Looking good. I can sort by the row name if I want to. All of that good stuff. But here's the important part, is that when I run that code, it helps me write the code. So here's that object. That object's currently stored in memory, but if I forget to write down this code, every time I want to use this data, I'm going to have to go through that whole process. But if I write down the code, and let's say I've restarted R and all of my data is gone, all I have to do, run that again, it's back. So really handy piece of code. Next, talking about file compression. A lot of the data that we use in R is actually, in biology, and in R in biology, is actually just text. Even like my gigantic variant files that are filled with all of these different SNPs and indels and all these other mutations, they're actually just stored inside of a big table coded using text. And I can actually open it. Well, if my computer has enough memory, I can actually open it. I have to specify memory because my files tend to be on the multi-gigabyte size. But as long as my computer has enough like space to hold it all in memory for the moment, then I can visualize it. However, that's not super useful. I often, I don't always need to just visualize things directly. And so a lot of the files that we will get will instead save room on your storage in the computer by compressing them first. And so for the record, I'm going to change this before I release this video. And so this example will change. But basically, this is showing how I could copy a file from a shared directory on the EduPod to my current directory. So from this to this. It would copy this file and then I could unzip it. I'll probably make that a different code, but this is just showing how we can unzip things. Now, for the record, this code doesn't load the data. In fact, you'll see my object name is just file names because, well, it's not the data inside of pokey.zip. It's the file names that were inside, which I believe was pokemon.csv. This is a bunch of Pokemon data. You might be noticing a turn. Actually, Pokemon data makes a great biology data set, is what we will learn. This zip file is a form of compression. It's a very common form. There's other kinds. You'll see .gz files. That's gunzip. It's just a different compression algorithm. But a compressed file is not intended to be readable by humans, but it is readable by computers. And so we'll often refer to these as binary data sets because they're not text data sets. Most of the time when people are saying binary, they're really just saying not text is really what they're saying. All of the data is stored as ones and zeros, but not all of the data is intended to be like able to be translated into text. So it's to be honest, really just text versus not text, with not text sometimes just being referred to as binary. If you want to see the actual raw text of a compressed file, you can use read lines, or you can just like call head of the file itself. But in the end, it just looks like gibberish because it's not able to be translated into text. So it's just a thing to know. Our script files, for example, are just text files. They're text files that when I open them in R, because of that extension, so that .r ending, my computer knows how to interpret it. Now, one tip I have, and maybe pause this video here, is to follow this link and change your computer settings so that it always shows file extensions. I cannot tell you how many hours of time some of my students would have saved if they had just followed this advice at the beginning of the class. When you make your computer show a file extension, it will resolve a lot of the issues you have around accidentally trying to use a compressed file as a text file because it'll be obvious that it ends in .zip instead of .pdf or .csv or .txt or whatever you were trying to interpret. You need to understand what you're working with. Okay, so to jump over, after like the file stage, once I've unzipped things, at this point, we need to then start structuring them. And this is where we will be using this concept of type and class primarily. So these are two concepts that are very similar. So pay careful attention to how they differ and how they are similar. They're also complicated by sometimes they are the same value. So let me give you some examples. These are my data types. They are also the names of certain classes of objects. And so when I say like they have similar things, I'm meaning really, really similar. But here's the idea. Data type is how an object is stored in memory. So under the hood, it's all ones and zeros. So somehow you have to make a series of ones and zeros equate to the concepts of true, false, and it turns out logical types of data can also contain missing, so NA. So that's three different options. Well, it can't store three different options in just a 0 or a 1. Additionally, logical data can have additional properties like names of different positions. And so it requires more than just like one bit of information. It can't just be stored in a 0 or a 1. I think they use 4 bits. So 0, 0, 0, 0, or 0, 0, 0, 1, or 0, 0, 1, 1, and so on. It uses these different pieces of information to store logical data alongside some different possibilities. But logical is still a very simple type of data. It's only got 3 possible values, and then it also allows you to store some extra information alongside it. So that's how we define this type of data stored in memory. Now, this type of data can be in all sorts of different arrangements. I can have it arranged into a vector, so that would be the simplest type, the simplest class, simplest organization in R is a vector. There's no like 0 dimensional. There's not just like a point value. Everything has at least one position. Um, I could also, however, have an integer, which is similarly like constrained, except although actually I guess at this point it's nearly infinite in theory, but integers are whole numbers. Now, it turns out it's not all whole numbers. It's not an infinite series. There's only so big of an integer as you can get, but it's most of the lower integers. Most. I'm sorry, I'm dealing with infinites here. I'm not a mathematician. I'm doing bad talking about this. Let me just move forward from this point. An integer is going to allow you to store a number as a whole number. And that saves on some room. So like I can store the value 126 million in a smaller amount of space than 126 million point zero 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 zero. It just takes about half as much memory, it turns out, based on how they wrote the algorithm. It'd actually be more efficient than that, but that's how they wrote it. If we contrast that to the numeric type of data, which has approximately 15 to 17 points decimal places, that's why it's able to save on memory. Now, one nice thing is in R, you will rarely really need to worry about it. That pretty much the only time in my class that you need to worry about integer or numeric is whenever you are asked specifically, like what is the type of data or what is the class of data. But that's it. Factor is actually a specialized version of integer. It's an integer with extra information. So like it's only positive integers. So like 1, 2, 3, 4, and 5. You might store a series of 1, 2, 3, 4, and 5 in memory. But then there's like a separate piece of information that's associated with that object that defines like what each of those different values stand for. And so we use this when communicating categorical data. And this because like one thing I haven't talked about is like the history of R is it started really focused on statistics, and being able to communicate categorical data was really important. Additionally, the way R was originally set up, this allowed you to save a bunch of memory by treating character values, which are more complicated and store most symbols and letters and numerals together. It allowed you to treat data like that, but store it in a much more efficient way, like an integer. It turns out they've rewritten how a lot of that works in R, and so most things, most character values actually kind of already work like that. So it's not necessary from that standpoint anymore, but it is still used in a lot of statistics packages for communicating categorical data. Mostly you just need to know you should avoid it. It's confusing. It prints off characters, but under the hood it's stood for by numbers, so you can like do math on character values. It's very confusing. I don't recommend using it if you can avoid it. Numeric, I already defined. Numeric is a lot like integers, except now we have decimal values. We can only get so precise after 53 points of precision, which is approximately 15 to 17 decimal places. If you need it to be more accurate, you need to go into like specialized packages for doing very, very accurate math. Now, I'll be honest, I have only a handful of times, although I've added to that handful recently, needed to worry about that level of accuracy. And most of the time, I just chose to make my calculations require less accuracy rather than dip into those complicated packages for doing much, much finer mathematics. But most of the data that we'll be using will be operating as a double precision point value or double. Numeric and double will be used interchangeably. Type of returns the value double for numeric data. That's why it's mentioned here. A character vector is one of the more common types of vectors that we will be working with. It allows you to put like letters and numerals and symbols together. A string is how we'll sometimes be referring to a character vector's value. Yeah, that's it. A list type object is more complicated than the rest of these. It is not an atomic type. So all of these cannot be divided further. That logical, there's no like simpler type of logical. It is indivisible. It is atomic. Think of the concept of an atom. It's indivisible. Not true, but there you go. I guess these are ones and zeros under the hood, so you could always divide it into ones and zeros. But a list is indivisible in a similar way as that metaphor. It is not divisible in similar to that metaphor. And that's because a list is like a series of containers. I have the series of containers. So like if I just had a jar at position 1, a different jar at position 2, a different jar at position 3, there is a difference between those jars themselves and the contents of each jar. I could have a peanut butter, I could have a jelly jar, I could have a olive jar. All right, I'm listing all the jars I know. But inside of those things are different types of data. So as a whole, it is a data structure. It is organized in memory in a particular way. But inside of each container is new properties. That's the idea of a list. And it's actually really important. It's the most common complex type of data that we'll be working with. Now, please note, these were ordered into a hierarchy. The hierarchy does matter when we start talking about data coercion, which we'll pick up with on Thursday. Data classes. Data classes are a little bit tricky because instead of describing how they are stored in memory, it describes how R will use it. So for our simple data classes, they're just the names of the type of data they store. So like all of our vectors, so our one-dimensional organizations of a single type of information, they're just the names of that type of data. So a logical data type organized into one dimension is a logical class. Integer type in one dimension, integer class. Same thing all the way up to character vectors. There's also a list class. It is also its type, so it's stored as a series of containers. Here I've color-coded each container. So let me just duck down. Here we have the first container, then a comma, second argument, second container. Third argument, third container, fourth argument, fourth container. I only gave a name to the second container. We can actually see that changes how it prints off. First container, just the square brackets doubled up, and then a 1. And there's a lot of helpful information in this. It's actually telling me how I can extract that data from the list. Super useful. We'll talk more about it when we talk about extractions. But that's a list. There's a particular class of lists called a data frame, which will be our primary tabular data set. There is also, however, a matrix class object. And a matrix class object is a single type. So I could have, say, a character matrix. Character referring to its type, matrix referring to its class, because I've attached the properties two-dimensional, having however many rows this is by however many columns this is. I'm pretty sure this is just all of the lowercase letters, so that's 13 rows by 2 columns. It may also have row names, and it may also have column names. But this is how I've made that code. So the matrix function, the data to store inside of it, so a character vector, and then I told it to make 2 columns. It also has a second class, and that's because all matrices are also arrays, which is just multi-dimensional single type data. So I could have a multi-dimensional array of a single type. And in fact, I have used that recently. It allows you to get really complicated data sets in a really small amount of memory. And so you can do math on it and do matrix math and multi-dimensional matrix math, which would be array math, not matrix math. Things like that. Quite useful, not so often in this class though. A data frame, however, all the time in this class. So most of the data we'll be using in this class, once we get out of this introductory unit, will be organized as a data frame. Now we'll often be accessing like one column at a time. So you have to know vectors, because underneath this, what's going to happen is the data frame. So data frame function, here's the beginning of the function, here's the end of the data frame function. Here's the first argument. Here's the second argument, here's the third argument. Each of those arguments, much like the list function, will become a different container. But unlike the list function and output, where all of these could have different links in addition to different types, This only allows for different types of data. It does not allow for different links. And that's because it has to be organized into a rectangle. Now, I did some fun tricks here. Like I said, A, B, C, and the number 4. And this turns out it's going to coerce, that's a vocabulary term, into a character vector that's stored inside of column 2. This will be a numeric vector stored inside of column 1. This will be a factor vector stored inside of column 3. We're going to talk more about this coercion later, but let's just come back to that at a later date. But this is how we can store information inside of a data frame, the data frame function. So definitely go through your script file, check that out, see how it prints. You can even see how to access different properties inside of it and even create a new column. But we're going to pick back up on that with next class. Here is a summary slide. You should know all of these properties. Like that is an important thing for you to know. But we're going to pick back up with data coercion. So thank you for your time, and I hope that made sense. Please ask questions if not.